Thank you, Matt. Good afternoon and welcome to Spirit Aerosystems presentation of their case study on aerospace engineering. As Matt said, I'm Steve Pryor. I'm the Director of Engineering for the Propulsion Structures and Systems business segment, and Joe Zinacek will be coming up. He's a Propulsion Structures and Systems Engineering Manager and Program Manager. Before I get into this case study information, Joe will be presenting that. I'd like to provide a brief overview of Spirit Aerosystems. Spirit is a global company with business segments throughout the world. We have approximately 14,000 employees. Revenue is approximately $4.1 billion, and we have total square footage of 14.5 million in 6 countries across the world. In the United States, England, France, Russia, China, and Malaysia. And we continue to build our product base and increase our presence throughout the world. Our product base is made up of 3 different segments right now. The fuselage, which focuses on building fuselages for Airbus and Boeing. We provide fuselages for Boeing family on the 737, 747, 767, and 787, and also for the Airbus A350. Most of our products is metal structure, but we also provide composite structure for the A350 and the 787 Dreamliner, which are currently in the process of being certified and built. Within propulsion, we have a very diverse product and very challenging product to design and build. We have very stringent requirements from our partners, our OEMs, from our engine manufacturers that we have to meet in order to provide a quality product to the market. And those challenges make it extremely challenging for us to be able to provide a product within the confines of the requirements. For example, like the outside surface is aerodynamically controlled. We have to design to that, but also be able to provide a product that is very close to the engine, in which we see high temperatures and high vibration environments. And also we have to provide a product that's acoustically treated as well. So with all those different constraints plus interfacing with the OEM, the engine manufacturer, and our partners and sub-tier partners, it makes it very challenging to get our product defined to meet the requirements that is levied on us. Our product is also on large commercial aircraft, Boeing. Also, we do business jets and regional jets as well. In addition to the fuselage and propulsion, we do provide support to our fleet through our aftermarket organization, where we have repair certifications capability to do modifications and changes to our product around the world. One of the challenges that we have are just like other business markets, where we have to get a product to the market as quickly as possible in order to achieve market share. So we have challenges that we face. In order to do that, we have to make sure that we provide a product that is good for the entire life cycle, design, build, and aftermarket, and make sure that it's at a cost in which the OEMs and our customers desire. Also, our OEMs require the product there sooner and sooner. So we have to come up with ways of how we can provide a product, a quality product, in a very short time or a very compressed schedule. And also, we are challenged with continual change type activity, working with all those, with the OEM, engine manufacturers, other partners, with interfaces and things of that nature. It makes it challenging to have everybody on the same page at the same time. So we have to make sure that we're working very close together and get the product that is required to the OEM correct the first time to minimize any type of rework effort that would be required at the OEM, which would be just more disruption for them at a very critical time in their program. But thus far, we've been very, very successful on meeting our customers' requirements and been able to supply a product on schedule to meet their deliverable requirements and test programs that are required. So to do that, we had to, with all the changes that we see and requirements and shorter time frame, we had to do something different within our engineering organization in order to have adequate time to come up with a quality product to meet our OEM requirements. And so we've been working with Realization to implement mainly on our C-Series program right now, and we're in the process of beginning our implementation on our Mitsubishi program and other new programs. So we're starting with our current new program business, and then we're also working with implementation here on our derivative programs with the 787 program, and then into our sustaining organization. In order to accomplish this, as been brought up a number of times already today, is the requirement of getting management buy-in. We had a number of meetings with our executive leadership, both within propulsion and our chief technology officer, to get their buy-in to go forward. So before we even implemented the process of critical chain, we have a meeting and buy-in from our chief technology officer, our vice president, general manager of the propulsion segment, and their executive staff to get the buy-in from the top as we go forward, so that it's being driven from the top down as what was been brought up already as being a critical element in the success of implementation. So with that, I'll turn it over to Joe, who will present our implementation activity.
Thank you, Steve. With this chart that's up on the wall, though, I've been pushing critical chain and theory constraints for 10 years plus. And so the day we signed that, I had to pinch myself. I'm still pinching myself that we're on this journey, and it's been exciting. But anyway, like I say, it's been a push, and we're finally started on the journey, and we're a little ways into it. So I'm going to try to clue you in on where we are in the journey. If I get the right button. Steve was talking about for the C-Series program. Typical program, we get the contract, we go out and do a joint development with our partner. That's a JDP, and then we go off to a milestone of preliminary design review, and then a critical design review. That's really capturing our engineering design phase, which is, of course, the typical conceptual design and then detailed design. Once we get a design drawings out there, ready to are released, our manufacturing engineers do the planning, figure out how to build it, where the parts are going to be built, and of course, then that drives our fabrication, tooling, and assembly folks. And some of our products are needed, especially like the pylons and the cells. We usually, on a new program, they have an engine development test program. And so we need that structure or something like that to test the engines earlier than the rest of the airframe for our OEMs. Not to slight, we have the supply chain there running in parallel up in the early design phase. They're helping us out with quotes, lead time for material. even costing for trade studies. A number of different activities are going on with our supply chain. And then once we get to needing detailed parts, a lot of it is offloaded. And that can be around the world. The parts can be as simple as a sheet metal part to something that is more complex that needs to be extensively tested, like a hydraulic hose or something like that for certification to be used on a commercial airplane. So the supply chain is an integral part and complex to integrate all this. We have new programs. They typically take 4 years. That can be plus or minus a year or two, and some of them get delayed even in that certification and testing part. We had, what Steve mentioned, a derivative program for 787-9 is one coming up. And that's essentially for us is such as they get a new airplane or an engine that they bump the thrust up where the loads will increase. Thus, we go back through the pylon or nacelle and look at those new loads, what the impact is, and some of the parts may need to be increased in gauge. So we may change 30, 40%. Not necessarily all the parts, but a number of the parts. So the derivative program is a new program, but not extensive as we're starting with kind of a blank piece of paper. And then we have fleet issues. A lot of times that's something out in the fleet that's annoying some of the airline customers. And so within a year, our OEM tells us they want the investigation done, engineering drawings incorporated into production, and then drawings and parts to support a service bulletin to the fleet. So that's overall for a program. Also challenges in execution. During that design phase, it's an iterative approach. We get a number of engineers, design engineers, stress engineers, analyzing it for loads, and then we have systems engineers. My background is design engineer of structure, so of course I think I'm the most important. So we fight with the systems folks, and of course the stress always rains on everybody's parade with a new requirement or more conservative sizing of a part. But anyway, we don't get it right the first time. We have to go around and around in a loop. We'll fix one area. I think we have it set, and somebody will come in and say, no, I need you to change that area. You need to move this fastener, this part. So again, that throws us into a little bit of tizzy, but there's just one of several. Next, we have a number of resources that are dedicated to programs, but we don't have, like any case, a matrix organization. We have some experts that are shared across programs. So again, these experts being shared can cause problems. In fact, we had a materials processes and systems engineer that reviewed and signed off drawings, and he became basically our constraint, and his time was really valuable, and we were all fighting for who was most important to get their drawings reviewed and signed. So. Also, coordination with your OEMs and partners. The OEMs, a lot of them are overseas, not in the same time zone. They're also, like say, different countries bring different cultures. And some of our partners, we have engineers in Moscow, work for a company, Progress Tech. They help us with our engineering, a little bit extra capacity. Of course, different time zone, different language, different... just conveying back and forth is a little tougher. Also, like again, our supply chain is around the world, and so some of the testing for the certified parts are done in France, or who knows, well, maybe the parts are not certified and tested there, but they're made there, and then we bring them typically back to the United States and test them in our test labs around the country. Oh, and in addition to our OEMs, they have their major sub-suppliers and some of our competitors. And also being first up on the agenda to support engine development programs, a lot of times we're the first people to release within our drawing in the OEM's processes and data vaults. So we're kind of the guinea pig for the rest of the folks, and we're out in front helping develop processes. And so far in every new program that I've been on, they changed the modeling computer program, the database. Something has to change. You can't leave things alone and use what you've been using in the past. So again, it adds up some complexity. Last but not least, within our own internal company, we have our integrated product teams. which is our supply chain management, assembly, tooling, fab, ME. And it goes back to way back when, if everybody's in their silo, design engineers or engineers develop a nice part, throw it over the wall, but unfortunately it can't be built. So we try to break those walls down, but again, they still exist, and communication and getting everybody coordinated is a tough thing. So all this leads to some pretty severe desynchronization within our world. Engineering, of course, like I say, the center of the universe for me, has a significant impact on our business. If we have engineering delays, that means engineering labor costs go up because we're going to throw overtime at it, we're going to throw extra bodies at it. Whatever it takes, we're going to do that. So, and then when we are late, then everybody downstream has to make up the difference. So that means a lot of expediting costs. Supply chain pushes off to the suppliers' demand expediting fees to come in quicker. So then there's extra costs there. In addition, the program downstream, you just don't affect the program you're on. If you have a delay, we were already counting on those engineers going to the next program. Well, if they can't go to the next program, then the next program's getting hurt also. And that happens quite a bit, and it's tough on the resource managers. Sustainment, a lot of times scope gets reduced, and we end up fixing something that should have been fixed up front after we release and before it gets to delivery. So again, there's rework and cost there. Delay penalties. Right now in our contracts, we don't have penalties for being late. We do have penalties on scope for being overweight or something along those lines. And in my mind also, it's a penalty of our loss of credibility in the marketplace for being late. We are on the verge of possibly getting a reputation of being late, and that's something we want to avoid at all costs. Again, lost throughput is if we're delaying, engineering needs to get on, and other programs. We've actually had to turn away a few programs because we did not have engineering capacity. So that's really painful for the top folks. In addition, the delays for the operations world, there's quality issues. They cause scrap and rework. If we have a defective part that does escape, then it takes a long time to get it fixed, and then they're thus writing rejection tags and doing a lot of paperwork to keep up with that. And again, with those parts, you're doing reworks, retooling. A lot of times we should fix something now, we push it out, and not do it right away. We'll do it later. Of course, later comes many years later. And last but not least is there's a lot of stress and firefighting within the engineering ranks. Kind of to cap on this, on some of our old lean training, we had, if you had a problem early on and engineering catches it, it's not very many dollars to revise the drawing. But once parts are made, the dollars go up, and especially if something goes out into the fleet, the dollars are really significant to correct it. So we want to do things right, and we want to do them early up front to avoid all that downstream possible impact. The new program, the C-Series, this is not a picture of their actual products, but it is one that we are currently in production. Again, they'll something similar. This at the back end attaches to the wing structure, and on the bottom the engine hangs onto that. And then, as you can see, all kinds of systems are feeding the engine. Our electricals, hydraulics, pneumatic. And again, buried in that is a thing we call the torque box, and that's the primary structure. For C-Series, for the fan blade off test, that we'll talk about in a little bit, it's 21 major parts, and a lot of them made out of titanium or steel forgings. So some pretty significant structure. Not shown on this picture is some composite fairings that cover that all up. So this all blends into the wing. It's the most important part in the airplane. Keeps the engine there. So anyway, our new pylon business requirements for this is the overall. We in the past best for like a fan blade. Our first one's a flight testing vehicle. That's our first production. We've done it in about 21 months. We need to do it in 16 months. We need to decrease by 5 months, about a 30% decrease in cycle time to meet our requirements. In order to deliver the first milestone on time, engineering part of it, that was all the overall, engineering plus our fabrication, all that. Best was doing about 12 months, and this is for it's a fan blade off test. It's where they let a fan blade on the engine loose, and then you try to contain that fan blade and make sure the pylon holds on and doesn't drop the engine and hangs onto the test fixture. It's a pretty violent test, and that's one of the first tests they're going to do with our hardware. And in fact, it's in the critical path for the airplane to have that test completed. So we need to do it in 7 months, and we kind of already went over cost on the conceptual development by a number of hours. So we need to, what's left over, do it in 15% less cost and 5 months faster than we've done in the past. So we need a throughput increase of over 55%. A number of programs that we're doing. The first two bullet there is our event is for some systems test hardware. And then the FBO was that fan blade off hardware that I was talking about. And then the last is flight test vehicle number 1, which is essentially it's the production quality hardware that we have. We're going to look at just the fan blade off, event there. We know when the delivery date is. We got that. So from that, we figure out when the assembly date is. We know what the flow is. That pretty good. And we try to really be really smart and exactly know where a part is needed within that assembly, which that assembly is only maybe 50 M days, maybe 8 weeks long. And from there, we back off and know where every part should be ordered in order to support that assembly date. And of course, our assembly people don't trust engineering, so they add pad. They don't tell us, of course. And our supply chain folks, they don't trust us either, and so they add pad. And so this is for a whole bunch of parts. In that little pylon, there's 1,400 parts for the C-Series. So and that's including fasteners and a number of parts, but we have a lot of parts. And I like to say we kind of like measure this with a micrometer, mark it with a crayon, and like cut it with an axe is what we eventually do. So we're not too. We try to be really accurate on all this, and then we don't have the mechanism to make it that accurate. So once we know their need dates, engineering, we got to get in there, and we kind of spread our workload out so that we know when things are due, and we may do some things early and some just on time. But in what happens is some of our events don't release on time, so they get gathered up on top of events that are currently we could release and make it on time. So thus we have a lot of confusion what the priority is. Do we work on these late parts? Do we work on this part that we could maybe get in on time, make our metrics look a little bit better? And it's not just in the engineering world. Then that drives the problems, in the whole supply chain. Our procurement, everybody, they're confused. What parts are really important once you get them late? And we've had them significantly late, so there's been significant confusion and daily meetings tracking parts. And especially painful if engineering's not released yet. So again, the previous date, we subordinate each downstream activity part by part. They controlled, or we worked it, managed it. Now what we do to decouple is batch the parts and then track that group of parts to one date, and then the downstream, once we release within the buffer, they pick it up and run with it. So we're batching and controlling less things. So we feel that's and we're working early as fast as we can. Thus, it's really not a concern. The folks downstream don't quite believe us yet, but since we're releasing early, there's not that direct connection. When we got realization in, we were trying to do it for the whole Spirit Wichita division, and at that time it was really going to be a big implementation, just focus on engineering. That did not work out, so we scaled it back and did it just for our propulsion structures and system business unit. And so since we scaled back, let's do the whole thing. And I was kind of, let's sit back and see what happens, because I knew engineering we could do it, but doing the whole thing, I was really curious how we were going to do that. Well, they came up with this model, and it's a pretty good model. The engineering up front, I've just said we batch our parts and use Concerto to set our priorities and our buffer. And then those parts, once they're released, our manufacturing engineer kicks them out to the next folks downstream, and they enter it into our SAP system and let the internal SAP system drive the parts. There's a few parts that may not fit that are long lead. We will track those in Concerto and track the exceptions. The unique point here is the very end. We are driving all parts to one due date, not a bunch of dates within the assembly process, to one due date. And then we'll have a full kit monitoring period of 3 weeks and drive to that assembly full kit point. And then assembly gets their time, and then we'll have some buffer at the end of the assembly. And we know, I can already see it, they're going to get parts, they're going to want to start touching parts and putting parts together. We're not to that phase in the implementation, but hearing other people, that's probably what we're going to have to really fight that one. So the mechanics, as soon as they get a part, they want to go with it. But I guess we'll have to lock them up. So that's the model, the new model we're working to right now. And like I say, we're just up in the engineering part at this point in time. We have not really released parts to be built at this point in time. For the engineering to reduce the WIP, we had a number of deliverables, and the different colors up here are tied to some of the test hardware. The darker blue is some of that fan blade out hardware, and then it rolls into the lighter blue is our final production flight test vehicle. The blue on the very, very left, that is some systems type work for test. So we got kind of a mixture of test type hardware, some production hardware, and we broke them up into work packages. And the work packages are, again, tied to the deliverable, and it may be a combination. Like work package 1 and 2 were too large. Work package 1 is predominantly the fan blade out torque box, which is the primary 21 pieces of primary structure, and then work package 2 is some of the secondary structure. And so it was staggered in this manner, and everything is staggered to the left far enough to support our due dates. And the whole idea was we reduced the WIP by 35%. No more than 4 packages are in work at any one time. As you'll notice, though, the work package 7, the yellow one on the bottom, is our work package to keep the pilot lit and things going. That's interfacing with the customer. Some of the other customers are working on their production configurations. So this is to keep up with the other folks on their production interfaces with us, Spirit. And they take also the interrupting phone calls, interrupting issues and questions. So work package 7 is kind of a collect-all, and we're kind of watching it and concerned that we could misuse that work package. And we probably have a little bit. How did we model it in Concerto, the engineering part? We have a high-level program as a super project with only customer deliverables as milestones, and that drives a project buffer. So far, that's been in great shape and it's been kind of behind the scenes. We've been very deeply into the work packages. Each is a sub-project with its own buffer and full kit points. And I'll show that in a little bit, our performance on those sub-projects. And there's another task model at a level so we can get synchronization between our design engineers, stress engineers, and integrated our product team. And that's IPT review, integrated product team review. It's a very small test, very short, but with realization we felt it was important that we model that to ensure the synchronization and communication was happening at that point. And again, we did the individual dates. Everything's the work package has one due date, and that drives to one due date on assembly. Our validation also happens to happen with the work package completion dates. Again, to pick out those exceptions that don't fit into our plan. And it's a big change of how we're doing business, because we used to have a process of getting the need dates and what the engineers would offer, and then we would negotiate. We'd go into a room for about a week, and everybody would play poker, basically, of what they could and couldn't do. But now we just need those need dates and validate that we're releasing plenty early, or we'll put those items that don't fit into Concerto. Some things have to change in the organization. We had our managers split up now, showing of what work packages they'll support. The top one is the stress manager, and he's got a couple of work packages of his own, and then he'll be supporting the other ones. We added a manager on to keep the whip low on the managers. Down below is our lead engineers, our stress and design leads, and what work packages they're going to be working on also. Trying to make sure that we got all bases covered with the low whip. It has caused some problems with doing performance reviews and that type of stuff. Now the organizations are a little bit more fluid, with people kind of arguing, are you in my org structure, or what? Where are you? So we can't keep up fast enough on that. So we're still learning that. Realization told us that we kind of tested them or taught them a few things on full kitting. We started off, and our engineer said, hey, we got a full kit. Well, it turned around, we did not have a full kit. I guess we have enough complexity and enough different experts that we did not agree on what a full kit is. So now we have a process that we identify what items should be the full kit, and then we're going to get our experts, a lot of folks that are senior, been there quite some time, agree these are all the items that you need to do this work. And then, of course, we get with the customer to buy in that these are the items we're going to be asking you for, and this is a timeline. Eventually, we get the kit full, or the full kit manager accepts that, and we put resources into full kitting. We have a hard time getting resources, so some of the program managers and chief engineers wanted that included. And then again, we'll review the full kit and feed it into the system according to how full the kit is and what the whip control dictates. And doing our scope management, there's always a lot of changes. It's an evolving process. Trying to get all the requirements up front is very, very difficult. I always said, hey, if you did that, your book would be like really tall and nobody would read it. So we try to do it the other way, and then there's always open to interpretation what is included, not included. We believe when we're implementing change comes in, we want to evaluate the change and incorporate the change based upon buffer control. So we want to manage the change much, much better than we have in the past. We want to do this coming through one control communication point, and again, change the culture to people. A lot of engineers now, somebody asks for a change, yeah, we'll do it, and so their business sense isn't quite there yet. So we want to get that under better control. Emergent work, again, we plan for the next month, identify the impact of the emergent work, and then replan and add capacity. This is our work package 7, where that emergent work's in. We want to cut down that multitasking and where like things that just are popping in and out. Put it in there, take care of it, or put it in its right priority with a drum buffer rope type implementation. Of course, I can't forget the customer, our OEM, and we had a good job on getting buy-in on this. Our realization team went to the OEM and did a workshop, and the OEM bought in fully and was willing to support the methodology. They were so supportive, they wanted some weekly updates on the charts, and make sure I get them all right. They wanted a chart on the full kit status, a chart on what help was needed, and of course then what was going on in Work Package 7. Work Package 7 was the direct link to the customer, so they wanted all that visibility. So again, with that buy-in, we get a early on, we had the customer talking to everybody and everybody talking to the customer. So we tightened that up on the first bullet. The next bullet, again, they were really into measuring every part due date. Convinced them that just measure the throughput and we'll be okay. So they let loose of that so far. And then, of course, resolving help needed. They bought in that they would help with the concerto priority and the full kitting needs. Last, there is help to incorporate work on the right work packages with minimal buffer impact. And knowing increasing WIP is not seen as an option for buffer recovery. Again, I think this is a challenge that we'll have. They're very understanding that we stopped work on some work packages. I think that's a pretty big step for most customers. They say, okay, we're not going to work on everything at the same time. We're going to stop some of it, and they bought into that. So that was a very successful meeting and workshop with our customer. We measured the throughput to see how things were going before. I was under the belief that buffer control would take care of it. Our realization guy said, hey, we need some throughput measurements up front, make sure things were working. And the blue line is a line that was a very aggressive target. In fact, some of the folks says, there's no way, you're making me buy into an impossible task. And I did find out working the realization guys, if they don't like the answer, they'll ask you a couple different ways. And finally, you will agree with them. Anyway, they convinced them to accept that new target, and they were right. Here's the latest throughput. We're completely through, and this was submitting our drawings for review to IPT, the Integrated Business Team, our product team, to review it. So we've met our throughput 3 weeks early. So there's great success, and like I say, sometimes I got to pinch myself, see how this is working. Not quite the resounding or great success on our buffer charts. We got to the left upper is the work package 1, the torque box. The next one down is system brackets. The upper right-hand corner is some systems, tubes and routing, or tubes. And the last one is stress optimization for the production torque box. The upper left, it went way straight up, and we found out one of our managers was feeding WIP in behind us. He was bringing in production changes into the test hardware. Later, our engineer said, well, we don't design test hardware. We design production hardware. So they had that focus. Everything was going to be production quality, and we're going to get as much of it in as we can. We had a non-advocate review and says, look, there was like 2 paragraphs of requirements. Be such a stiffness on the hardware and hang on to the engine during this test. And that was like 2 paragraphs for requirements, but they've expanded that in their own minds to something much greater. So we did get them off of that and recovered the buffer and arc in control. Another thing that helped on that was we had 2 lead engineers split up the WIP, and they started teaming and working better together on the work package. The one in the bottom, it went up because the one up in the right, some of the systems, that was part of that full kitting problem. Some of the full kit was not ready, so we took resources off of that work package and moved them over to help on the one in the upper right. Once we got that back, they got their buffer under control. The one up in the upper right, I'm accusing them they're connecting the dots and go make a picture. I don't have a clue what picture they're going to make, but anyway, that was supposed to be a joke. And back to some of my earlier training, I always saw those nice little charts that kind of edge up to the upper right-hand corner where we did a complete loop and everything else here. So, and the one on the far right-hand corner, they said they're trying to make a dollar sign. So, anyway. For full kitting, on our second, we have a second new pylon program. This is really important. They looked at their full kit, decided they did not have enough full kit to proceed with the work. So they held off for 2 months before they started work and focus on full kitting. So they're currently working on this full kitting, but it is huge because before they made that realization, they were yelling for resources and saying, hey, we got to get going, got to get going. Well, now it's like, you need to work on your full kit. Then we'll give you some more resources. And if we would, in the past done, we would have gave them the resources, and we'd probably steal them from other programs that needed them just as bad, such as C-Series. So again, knowing when to start work is just as important as doing the work.
Some additional benefits that we've seen with the implementation of critical change is early identification of problems, as depicted on those 4 charts. It indicated we were notified or brought to our attention, management's attention, that there was requirements that were missing, like Joe said, full kitting, information that was needed from our OEM wasn't there, and so we were able to bring the attention to management. Management was able to put the appropriate attention on it to get the resolve in order to move forward. And as Joe also stated, staffing on the full kit, not staffing up those programs early, in which we would just be spending budget and money that we'd need later just to staff up the program because they needed it, but with the full kit there, we were able to put off on staffing and apply the appropriate resources there to address the needs. Other things, identified gaps in our program between our program management and resource capacity. It also emphasized the need for additional resources. We got to a point where we had to get releases out. We were able to bring in additional resources for that last period of time rather than bringing a lot of people in for a long period of time. We were able to bring in people for a short period of time to address the issue and move on. And then also the ability also to bring in our technical leaders, our associate fellows, to be able to look at the product or the data that we had to make a determination, do we have the appropriate full kit in order to move forward. So with those benefits, we've also had some obstacles and challenges that we've had to overcome. On the fan blade out, we had to correct that obstacle, create work production issues and interfaces there. Engineering the whip that Joe brought up, we had to limit that additional whip from coming in. Like you said, there was just 2 paragraphs as far as requirements. We did not need all the additional ones. We like to do a production type hardware, but the requirements did not dictate that. And then also some other obstacles, the full kitting, moving resources there. Also on the implementation, managing only the exceptions in Concerto. And then also the other challenge that we've had is the other organizations that support the IPT. With this new business model that we're going with, we've had to change the way we operate as an IPT and allowing other groups to change the way they've been doing business and come in and look at it in a different way and help us managing and implementing our products. Lessons learned. Whip control is very important to focus on that. Effectively reviewing the status, looking at the buffer and where it's going, engaging the customer up front so that they're aware of what we're doing, and then also engaging the other support groups of the IPT, the product definition group, change board, supply chain, and so forth. So I went through that kind of quick to get us somewhat back on schedule. So I don't know how much time we have for questions now.
Maybe in the interest of saving some time, if you have questions for Joe and Steve, feel free to find them. We'll have a coffee break in about 45 minutes and also some opportunity later tonight. But I don't know if you caught this detail, but this is a current implementation, and they've seen a lot of success very quickly. I think we've completed 2 of 3 stages. So thank you very much for sharing that with us.
Thank you. In addition to Joe and myself, I'd also like to recognize 2 other of our core team. Carolyn Vanderveen is here, and also Keith Ingo, that have been very key in our overall implementation of realization. So, thank you.